Joe here, everyone. So this should be a very interesting talk today. Joe's coming to us from Canberra, Australia, where she's at the Australian National University. And as you may have noticed, her subject field is not traditionally speech and language technology, but it's actually astronomy. And one of the things I'm most excited about is the fact that nowadays people outside of just CLSP are caring about language technology. So we're getting all kinds of astronomers and others that are really interested in our sort of work. So there's some cool interdisciplinary collaborations going on here. And I'm really excited for her talk. The first thing that, of course, that jumped out to me was AstroLLaVA. And if you're thinking that AstroLLaVA is probably just applying Llama v2 to astronomy data, you're actually wrong. But no, it's actually correct. So yeah, but I'm really excited to hear her talk about
Llama that went to space.
Ooh, yeah, I think that's what the picture is on the paper. But yeah, so excited for Joe's talk. So please welcome Joe.
Thank you so much. Thank you so much, Kenton, and thank you really everyone for having me here. I'd also like to thank John for having me here and Josh, and super excited to learn about everyone and your research. So today I'll talk a bit about the consortium that I'm a part of. We are called UniverseTBD, and we stand for Universe to be decided. When we chose the name, we thought about it quite deeply. It was like, why go for something certain when the world around us is quite uncertain? So we adapt as things change around us. Specifically, today I'll talk to you about our research with foundation models for astronomy. Okay, cool. But before I start, I would like to start with this slide. Coelorum perupit claustra. This is written on the epitaph of Sir William Herschel. These words mean that he broke through the barriers of heaven. And in my life, I've had two moments when I thought that I almost did the same. The first time was when I was 6 years old and I saw a solar eclipse reflected into a bucket of water back home in Romania, where we didn't have much. And many people around me told me that I'll never be an astronomer. And then yet I'm here with you today. So in a sense, where there is a tool and there is a way, we can make things happen. The second time was when Kartik here and I were sitting at the Flatiron Institute almost 8 months ago together and thinking, how can we use this new technology in large language models and foundation models to truly open up our field to the world? So that's how UniverseTBD came to be. We are pretty much an AI research lab. I like to call us an AI research hack lab most of the time, but my more ethically concerned colleagues would like to go for this denomination. We have 30 plus people working together to democratize astronomy for everyone and science for everyone. We are a bunch of people coming from all walks of life. We have astronomers, software engineers, computer scientists, NLP experts, and we are growing. So we're very excited to present what we've been working on today to you as well. And then we also have 4 continents and counting. So we have people from everywhere. We have Europe, India, China, America. And it's a pain to set meetings up, but we make it happen. So I hope that says how determined we are to make this dream come reality. So now you might ask yourself, what dream are we actually talking about? So our dream is sort of reflected into our mission. So our mission is to democratize science for everyone. And what do I mean when I say democratization? I mean the problem that we face right now in our fields and in our research and in our society to some extent. So there is a monopolization of scientific resources that reflects in an opportunity gap around institutions. Many people that come from smaller institutions, also in countries without the access that we have here or in Europe or in Australia, don't have the same access to resources that we do have. So what can we do to help them? It is very likely that as technology advances, this gap will likely increase. And I would like to be proven wrong, but until then, this is a problem that we have to think about deeply, that what can we do to actually stand up and try to do something that will change this problem. So to get to that point, we started with a small goal to build a little model, the AstroLLaVA, but our goal we have a larger goal in mind. We want to build semi-autonomous AI systems capable to aid researchers everywhere. So we do not want to replace human beings. We want to empower human beings to do the best research they have. And we also want to empower enthusiasts to engage with our research in many meaningful ways. You might think about it, why start with astronomy? because we are astronomers, it's the easiest thing we can do, but also because astronomy is a quite a unique field in that we actually work with data sets where we can explore and experiment and not be afraid to be sued a lot. So, for example, astronomy has the simplified privacy management structure where privacy is not quite the same problem as it would be in medicine, for example. It is broad appeal. Astronomy is the oldest science on the planet. We've done this for many millennia, and people everywhere want to look up and understand what's happening with our universe, so we can appeal to a broad audience. Astronomy is a rich resource for innovation. We have a lot of data. We have data from space, we have data from ground, and these data objects are actually quite unique. We have images, as you'll see today in my talk, we have text, but we also have time series, stellar spectra, and so on. And finally, and the reason why I'm happy to be here with you today is that we are a very, very large community. And right now we are a community that wants to jump in and connect with other communities, especially in the computer science field. We want to keep growing and build interdisciplinary solutions to the problem that I talked to you about. So where do we start? We start with natural language processing, because that's what inspired this work. When ChatGPT came to life, I was very, very particularly impressed with that solution. Not so sure at the moment, but then I was very impressed. So as part of UniverseTBD, we have two tracks. We have the research track, and as part of the research track, we have developed already the AstroLLaVA 1 model, and I'll show you a few more details very soon. But we also have quite a large project going on at the moment called scientific hypothesis generation. It's called Hypogen, and one of our junior researchers is going to actually give a little talk himself in my talk. And then we also have the community track. So the goal here is, okay, we're building all these models, AstroLLaVA. I forgot to mention AstroLLaVA. We also have a multi-modal large model that we're developing, Hypogen. How can we use these models to help the community around us? That's why we created a community track as well. And one of the projects we're considering at the moment is adapting these large language models to help researchers that have dyslexia or other silent challenges that affect their research. Okay, so where do we start when we think about NLP and when we think, I guess, more generally about artificial intelligence? And I would like to start with the work of Dr. Alan Turing. So in 1950, Alan Turing published this paper in a journal in psychology, actually. So you can see how forward-thinking he was at the time and how far ahead he was thinking. And this paper, Computing Machinery and Intelligence, in the very first sentence, poses this very important question: can machines think? And to answer this question, he proposes what we all know as the Turing test, whereby you have a machine and a human evaluator, and the human evaluator only sees the machine and the human interacting via text. The evaluator knows one of them is a machine, but doesn't have much more information than that. And it is said that if the human cannot distinguish between the machine and the human, then the machine will have passed the Turing test. It is very hard to explain this while you're a bit jet lagged, but I hope that kind of gives you the gist. All right. So what happened, after 1950, we had 1966. This is Joseph Weizenbaum of MIT. He actually made this chatbot called ELIZA. So I want to demo you a Java implementation of the chatbot that he came up with. And in this chatbot, you talk to Eliza, Eliza says, I'll be your therapist today. And you say, well, I'm feeling quite nervous because I'm giving a talk in front of an audience that's expert. And then Eliza comes to me and says, did you come to me because you're feeling nervous? Yes, pretty much. How can you help? I mean, how can you make me feel better? And then it goes passive aggressive on me. Don't you believe I can help? I can, but how? Have you asked such questions? By this point, I am more traumatized than when I came to Eliza for help. Right? So this is problematic. Now, fast forward to 2023, I go to GPT-4. I say, maybe something has happened in the last 50 years that can help. I go to ChatGPT and I say, I'm feeling quite nervous today. Now, ChatGPT, I think running with GPT-4, has already validated my feeling. It is already, it wants to help. I tell ChatGPT why I'm nervous. I say I want to see how I can use large language models for science. And I know I type very slowly. It tells me I'm feeling overwhelmed, and then it gives me solutions. So after the interaction with GPT-4, I feel better, dare I say. Okay, so this has happened. So we have 1950, Alan Turing poses the question, 1966 we have ELIZA, and then we have now GPT-4 running on a transformer. Okay, so what has really changed between these two moments that we just have observed? Many things have changed, as you keep seeing. If I was a PhD researcher right now in NLP, I would be much more stressed than when I was doing my PhD in galactic archaeology. A lot of advancements are happening a lot, very, very fast. So here I put just some big moments in the last 10 years. So we have 2014, the paper by Wachmann with neural machine translation. That was a very, very seminal paper for the field. Then we have 2017, Basmani et al. Coming up with a transformer architecture. Then we have 2018 BERT. And then, we have this plethora of both closed systems and open systems. On the closed system, we have the work of OpenAI, Google, and so on. But we also have the release from Meta. We have Llama coming up, and so on. And now we have also work from LLMs and Allen Institute, and so on. So a lot of models are out there. Okay, so what is at the core of why these models work, especially in models like generative transformers? Why do they work? So the response, I normally give this talk in front of an astronomy audience, but I know this is an expert audience, so I won't go too much detail. But we care about attention. So if I ask you this question, what is the sum of all red cards? Then you look down and you try to infer this sum and give me an answer. Similarly, a neural network that does the same, that starts to pay attention to different parts of the input, is called, it's self-attention. We have this self-attention mechanism. Okay, so the first revelation is that we need this sort of advanced attention mechanism that can pay attention to different parts of the input in order to achieve some goal, right? In here, in this slide, what I wanted to show you the difference between modeling and learning. So transformer lines towards the learning part, towards the learning spectrum. And by learning, I mean these models really are data hungry. They learn, they don't have too much inductive biases, as for example, linear regression model, or even a CNN, right, where we have make some assumptions. Or even here, I put a binary orbit where we can parameterize the system incredibly well. Okay, so the first thing is we need attention. And then, of course, we have the paper, attention is all you need, in 2017, 70,000 citations. That is a great outcome for that paper. In 2018, we have BERT coming up, again, doing very well, this very nice large language model that really sort of precedes quite a lot of the work that we see today. But these models, these transformer models that are coming up in the last 5 years, are transforming not only the NLP field, or more generally, but even the computer vision or CS-specific fields, but they're also transforming science as well. So right now here, I'm just showing you a bunch of papers that we use in astronomy. So we have an astroconformer, we have galaxy morphological classification with transformer architectures. John has done a lot of work on galaxy images, so you can probably talk more about this paper. We have time series being modeled with transformers in astronomy, and even distinguishing planetary transits with transformer architectures. So we see these models coming back and back to life in astronomy, and we are adapting to them, sometimes in a better way, sometimes in not such a good way. But most of the time, we try our best. But at NASA ADS, this paper arrived, I think, 2 years ago, maybe I'm wrong, 2-3 years ago, called AstroBERT. So this was the first paper that said, okay, let's think about other modalities where we express astrophysical knowledge. And text came up as a really good way to do it. So then AstroBERT came to life. This model that was built by NASA ADS was used for named entity recognition in the NASA ADS corpus, which at the moment has 50 million scientific articles, is the largest one today and he's also our partner for UniverseTBD. Okay, cool. So, all right, so we need the maths, right? We need the attention, we need the maths, we need the people who work on these things at the frontier of knowledge. But what else do we need to make this really work? We need money. We always need money. Some of us need more money than others, but that's important because if you're OpenAI, you can actually try to, exactly what happened here. If you look at this plot, you have the ear, and on the y-axis you have the size, and you can see how how OpenAI moved from 1.5 billion parameters for GPT-2 to already 170 billion parameters for GPT-3, right? And training these models means that you need to have access to resources, GPU resources, which costs money. Okay, so second thing you need is money. And the third thing you need is human beings. I would argue that that's the first thing you need, but yeah, so third thing is you need human beings because if you let the model like GPT-3 or GPT-4 to do, to answer in the way where it's not aligned, what you might get out you might not like. So people have spent quite a bit of time trying to align these models to serve human interests, right? So, or at least not be toxic in many, many ways. Some of us might disagree how successful this is, but when you use reinforcement learning from human feedback, you can try to achieve these tasks. So you need maths, you need money, and now you need humans as well. And now we are in 2021 with InstructGPT. You all probably know this already, so I hope I didn't go too fast or too slow. Okay, so how did it affect astronomy? What's up with astronomy? Where does astronomy lie? This tweet came from Google, and Google released this BARD, in a way to compete with ChatGPT. And, they're very hyped about it. They're very, very excited about it. And then there was a human on Twitter, ex-Twitter, that asked, what new discoveries from JWST can I tell my 9-year-old about? And extra points for who gets this in the audience, that's really good. But then Bar responded with JWST to the very first picture of a planet outside of our solar system. Now, SDSTI is right here, peeps there might not like this answer, so. Okay, it is wrong. So what happened with the stock of Google when this happened? It went down. It went really down, actually. They lost a lot of billions that day. That is, if you're Google, you would blame this on astronomy. That's not good because people were like, you can't lie to me about planets. That's one that I won't take. Okay, so we at UniverseTBD were like, let's do something about that. So we were like, okay, let's move from a generalist model like BARD, ChatGPT to a specialized model that we can develop as part of our community. Okay. So that brings us to AstroLLaVA 1. So this is the first iteration of the AstroLLaVA model. And please meet AstroLLaVA 1. We spent quite a lot of time with Midjourney trying to get that, bring it to life. And here I would like to credit the amazing work of Josh Nguyen, who's now a PhD researcher at University of Pennsylvania. If you want to learn more about the AstroLLaVA, because Ben is quite close to here, I would actually really have him here to come give the talk himself. It's a really brilliant paper, and he has done a great job. And, I'll talk a bit about the details of the model in a minute, but then we talked about it on Twitter, because that's where all the information goes, right? Good or bad. And then we got a retweet from Jan LeCun, and then this has become LeTweet. So the AstroLLaVA and LeTweet are very, very proud parts of our portfolio. Okay, but how do you actually build an AstroLLaVA? So you have a base model, you have the resources, you have money, you have a lot of data, and then you have a lot of patience. You can wait for a long time to finish this training, and then you get a pre-large training model. So you're trying to predict the next token in a not regressive manner. With AstroLLaVA, what you have is you take the pre-trained language model and you adapt it to a data set that you have. And here I say small data set, but it actually should be smaller data set. So once you do that, you can do training with the causal language modeling objective on this small data set, and then you get a fine-tuned language model. So for Llama, for the AstroLLaVA, we use the Llama 2 model. We use the 7 billion version. At the time, we are now training 70 billion. We have trained, I think 70 billion has been trained. And now we have on this smaller model, we have used 300,000 archive AstroPH papers. So these are papers that we generally care about in astronomy, which resulted us in a minuscule data set of 230 million tokens. So moving forward, we have access to a lot more data coming up, so we can train these models much more. Okay, so with AstroLLaVA, for us, AstroLLaVA was the first step towards something bigger. And we just wanted to see what it does when we play with it. So here I'm showing you an original abstract in astronomy. And then you have three models. So you have GPT-4, Llama 2, and AstroLLaVA. And these three models just receive the same information. We prompt them with the yellow part. And then they complete the rest of the abstract. And when we look at the results, what we see is that, well, first of all, the AstroLLaVA is not quite as perplexed about seeing astronomy language as the other two. And in this, I know that we are not in astronomy, but for me as an astronomer, really what it comes up with is much more, the language that it uses is not quite as general GPT-4. It's much more specific. And even more importantly, is it fails in more specific ways. So it's much more detailed, even in its mistakes. All right. But evaluation is an ongoing process. We are also learning how to evaluate things much better. But before evaluation, I also want to talk to you a bit about embeddings at the level of the AstroLLaVA. So because we fine-tuned this model, we were able to actually get embeddings as well. And here you get on the x-axis the pairwise cosine similarity, and then on the y-axis you get some density in some beam. So here, what we did is that we tried to take any two abstracts and see how similar they are. And you can see with GPT-3 that shown in the blue bins, that you're looking between 0.7 and 0.9. So the way I think about this is that GPT-4 or GPT-3 in this case is sort of an island in the corpus of all the information that it has seen before. Whereas AstroLLaVA, because it has been fine-tuned for astronomy, sees more than an island. It's like a continent of astronomy, which is shown by this plot. But let me make this more specific. So here you have two papers, same with BART, right? So paper one talks about gyrokinetics, and paper two talks about modified Coulomb law. So GPT-3 similarity says 79%. It's like these two guys are similar, I'm pretty good with that. Whereas AstroLLaVA says not really. They're talking about different things, right? So we have 36%. So because we are in a continent, we can see how much further things are from each other. These two things are quite similar if you consider, I don't know, New York Times articles about, I don't know, something very important. Okay, now we have a different example here. We have paper one that talks about a nebula, and then you have paper two that talks about star formation in a region, in an H2 region. So GPT-3 similarity, for me as an astronomer, these are quite similar things. They should be talking about the same thing. They should be talking about what happens in the region of a nebula. Whereas GPT-3 similarity says 82%. So yeah, they should be similar, but AstroLLaVA says they should be much more similar because they are talking about the same. Yeah.
Can I ask a quick question? Are these held out documents or are they documents that were trained on the model?
So these are hold out documents. Yeah, definitely. We wanted to be as fair as it could in that sense. But we are trying now to take a smaller model like Olmo, where we know exactly what they're doing even before the fine-tuning step. Okay, thank you. All right, so going back to Google, now UniverseTBD come to life, but what happens to Google Store? That is exactly what happens to Google Store. We wish they would give us some of those funding ourselves, but we move on. Okay, so moving into the next part of my talk. There's this question about, okay, cool. So we have an LLM, a specialized LLM, that's really nice. Fine-tuning works. And Hugging Face transformers is an amazing thing, but can we go a bit deeper than that? Can we actually use these models to reason, to generate scientific hypotheses, which for a scientist and astronomer is the bread and butter of our jobs? literally. So I would like to introduce hypogen at this point, which is the hypothesis generation. And I just would like to show you these very two quick slides on hypothesis. So here I have told GPT-4 to only see 1 in 100,000 papers. And then through a RAG pipeline. So I'm talking to the model through a RAG pipeline. And then here on the y-axis, you have the evaluation score. So I said, come up with an idea, please. And then we evaluated on the idea that it came up with using human experts. And we saw that the quality of this hypothesis, is not improving depending on the number of papers that it sees. So this is very early work. This is not in any way statistically robust work, but we just wanted to experiment with GPT-4 at the time. And then we did a trick. And we asked another model to criticize the first model and then provide the feedback to the first model. And then we asked it to regenerate these ideas. So what we see that when we do this adversarial critiquing, the quality of the hypothesis improves. So we think that the feedback improves the quality of the critique, even in this very small, tiny test experiment. And this seems to actually also apply to the critiques. So the more papers he sees, the better the critiques become for the model as well. And okay, so we wanted to understand here, why do these hypotheses get better with adversarial critiquing? So if we can take all these abstracts, you embed them. So suddenly now they live in a very high dimensional space. And then you use some very simple projection into two-dimensional space. Here you have TSME in 1 and 2. And then you see where these papers kind of live in the embedding space. Oh yeah, I've done that. So what I'm trying to show here is that if you take a generated idea and you find the top 7 papers or 5 papers most closely linked to this idea, the more papers the model has access to, the more this idea can actually sample this space. And this applies the same with in here, we have for example, I picked here 1,000 papers, and then I have one idea that samples this sort of black contour. And then I told the model, please criticize it and regenerate my idea. So you can see how it kind of like expands its scope of it. And then I say, okay, cool, please criticize it again and expand your idea. And then it comes up with this green contour. So it seems that the more critique it has access to, the more it can actually expand into the literature and come up with different idea. And the same happens here. But my work with this very, very small experiment is truly just a very small experiment. And the work that's being done now by Charlie O'Neill, who is working with us at ANU, Australian National University. I think next year he's going to apply for a PhD. He's one of the most brilliant people I've ever met. And his project, Hypogen, is being supported by Tirthankar Gosar from Oak Ridge National Lab and Dr. Roberto Arellano from Meta. And I will let Charlie actually tell you himself what the kind of work he's working on. And I think we have some time.
Hey guys, today I'm going to be doing a bit of a speed run of some research we did last year, looking at how to make language models more creative and yet more reliable and accurate at the same time. And we do so with this thing called STEER. So the problem is basically that LLMs, as we all know, are capable of generating very creative synthetic data, but often that comes at a trade-off of producing synthetic data that is coherent. And we noticed this in many different applications, but one where it was particularly clear was generating scientific hypotheses. Methods to try and get it to be more creative and diverse, such as increasing the temperature, would obviously reduce the coherence of the language model. And we thought that there must be some way to address this that doesn't involve retraining the language model from scratch. And so we thought, why don't we just take the logits at the end of the language model and see if we can manipulate how we're decoding these somehow to produce data that's more coherent and more diverse. So yeah, this is the example of a scientific hypothesis. So for instance, if we drop the diversity right down, so if we push it back to the origin here, to get more authenticity, then we might get really authentic scientific hypotheses in astronomy, but these are pretty standard hypotheses that have been said many times, and it sort of just says the same thing over and over again. If we increase the diversity by increasing temperature and repetition penalties and all that sort of stuff, we get very interesting hypotheses like are black holes made of cheese, but they're not very coherent, they're not very good scientific hypotheses. So we notice this sort of Pareto boundary of the trade-off between authenticity and diversity, and we want to see if we can push that boundary out and get something that's both more authentic and more diverse. So in terms of background, there have been a lot of attempts to manipulate the logits of a language model in order to increase some dimension of the output. So for instance, classifier-free guidance, which originally came from diffusion models, upweights the importance of the prompt. So it looks at the logits with and without the original prompt and can subtract the logits without the prompt from the logits with the prompt. And that is a way of emphasizing the importance of what you're feeding in. And this is actually used in system prompts for many language models now. Contrast decoding, coherence boosting, context-aware decoding, they all involve some subtraction of the logit distribution with something and the logit distribution without something. And so, yeah, I guess the common theme here is steering the language model's decoding by subtraction. And remember, this is just the last layer. This is the logits that come out of our final projection. This isn't retraining at all, which is handy because it means it's available to people with not much compute. So our methodology and the key idea here is we want to increase the quality of two dimensions at once. So all the previous things we just mentioned increased one dimension at once, for instance, adherence to the prompt. So to do two dimensions at once, we sort of reasoned that we probably need two different types of subtractions. So if you imagine your real data distribution, let's say of astronomy hypotheses, being in some support in some high dimensional space, to achieve authenticity, we want to attract synthetic examples, our generated examples with the LLM, to that real distribution. And so our attractor here is what we call contrastive expert guidance. So all we do is we take a fine-tuned model, so maybe a model fine-tuned on astronomy papers, and we get the logits from that, and then we subtract the logits of an unfine-tuned model, so the same model, but unfine-tuned. And so what that does is it attracts the generated examples to that real data distribution. But at the same time, like we said before, if we attract too much, then we end up with examples that aren't diverse. And so we need a repeller at the same time, and that's negative prompting. So we randomly sample from things we've already generated and from existing real examples from that real data distribution. And then we subtract the logits of the prompt with the negative context. So in that case, we're telling the model to avoid things we've already generated. And if we can balance these two together, as shown by these equations here, so this is parameterized by two different hyperparameters, these subtractions. If we can balance that correctly, then we can actually, what we hypothesize that we could achieve an increase in authenticity and diversity at the same time. And so this is a little picture here. So this is the attractor. So we're making our examples more relevant to the real data distribution rather than the general distribution of language. And negative prompting reduces the likelihood of things we've already generated. So some results. So we tested this on scientific hypotheses, astronomy hypotheses. Jigsaw, which is a toxicity dataset of toxic and non-toxic online comments, and a common sense question answering dataset. And so we fine-tuned a model on this and then used our steer method, so the two subtractions when we were decoding, to generate synthetic data. And we did so with some other benchmark decoding methods such as top K nucleus and contrastive decoding, which are sort of state-of-the-art decoding methods. And we found that according to our automated metrics here, that we achieved high scores in both diversity and authenticity with our steer method, which was a good start. We also did some human evaluation and GPT-4 evaluation, and again found that for the right combination of hyperparameters that governed the attractor and the repeller, we achieved significantly better win rate against nucleus sampling with our steer method. A bit of a sensitivity analysis, which is just confirming that as we increase the attractor hyperparameter, that we get more authenticity at the cost of diversity, and same with the repeller hyperparameter eta, and vice versa. And again, ablation showing that there is a definite improvement when we change these attractor and repeller hyperparameters from 0. Another way to measure the quality of our data we've generated is with downstream accuracy. So if we can train a classifier on the synthetic data to do the original task, so for instance, jigsaw toxic comments, classifying whether it's a toxic or non-toxic comment, and then common sense Q&A, training a classifier to answer the question generated, and then having a look at the performance of that downstream classifier. It's another way of measuring data quality, perhaps a better way. And so we see here that STEER, the performance of the classifier and the question answerer, was significantly better than greedy, nucleus, and contrastive, although still not quite as good as real data, which is showing that there's possibly more to do. And this is sort of, again, going back to that Pareto boundary, showing that we've actually pushed this out. So for different combinations of the hyperparameters for eta and gamma, the attractor and repeller, we get a performance increase in both fidelity and diversity over nucleus and greedy. So why do we care about this? I guess now that we've got these really large language models, there's a lot of talk of GPU poor. If we can't afford to fine-tune these huge models for particularly long periods of time, we have to use smaller models and find ways to get more improvements out of them. And so we think the methods like STEER and this sort of decoding methods at inference time can be really important for generating synthetic data sets that are diverse and authentic at the same time. A follow-on from this is perhaps generating synthetic data sets that we can use to retrain these smaller models for recursively improving language models. And there's been some work on that recently as well. And yeah, in terms of additional work, we also see that other people have since done similar things to us. People are actually doing this subtraction not at the logit stage, but even in the weights of the model, in order to come up with task vectors. So it doesn't just have to be authenticity and creativity, which are dimensions. You can choose any arbitrary dimension in the model, and as long as you have a way to define that task vector, you can actually perform addition with those vectors and steer the model towards whatever dimension you care about. And so yeah, wrapping up, hopefully the logic behind this method, this brief introduction, gives you food for thought about how we can generalize this attracting and repelling idea with smaller language models, and maybe ask you to come up with some other ideas of subtraction which might improve performance. So everything from subtracting unconditional distributions to short versus long contexts, etc. And yeah, thanks to UniverseTBD, my supervisor Tang, and obviously Yuan Sen and Joe for all their assistance on this project.
All right, so we'll continue. So Charlie will probably do a US tour next year, and I would really, yes.
I just had one clarifying question.
Yeah.
The speakers not here, but again, speak on his behalf. Did I understand it correctly that you measure diversity here in your tables based on law?
So I think we measure diversity, as far as I remember from his paper, using a metric, a set of metrics that, yes, includes norm as well.
So one immediate concern that's here,
Yeah.
that these metrics, to the extent that I understand, they are measuring diversity in terms of shadow measures such as token diversity, the diversity of different ways that you phrase things.
Yeah.
But I think the kind of diversity that you have in mind is like how creative an idea this is, and these are very different forms of creativity, I think.
Yeah, your concern is very valid. We are actually, so this work has been done a year ago, and since then, Charlie has been working on the current hydrogen model, which we are actually hopefully gonna get a paper release for NeurIPS data sets workshop, where we create a scientific data set, and we also hopefully will provide some metrics that we curated to be able to evaluate on that data set. And with those metrics, we are taking this into account. And human feedback is part of it. And also we have a set of GPTs that also play a role in doing some sort of model evaluation themselves. So there is a lot of talk, thinking. Roberta is helping us quite a lot on the metric side.
Later on, next year, I would love to hear thoughts on how to do creativity.
Absolutely, and I would love to put you in touch with Charlie. He's really spearheading this effort, and he's a brilliant young person. So I think he would also appreciate talking to you. Thank you very much. Okay, so let's keep going because we have 20 minutes to finish quite a lot, actually. So AstroLLaVA, we have AstroLLaVA, now we have hypothesis generation, but we also thought about doing something fun to give back to the community that wants to sort of engage with our model. So for this reason, we thought that a picture is worth 1,000 words, so why not go to the beautiful images of galaxies? So here we talk about the LLaVA model. The LLaVA model is a clip encoder, that's hooked to a decoder, an LLM. And then what happens here is that you have this vision encoder having been frozen, but you have this connector part here. You have this vision language connector, which is very fancy matrix. And then with this matrix, you can actually sort of change the weights in such a way that you can connect these two modalities in a latent space. And then the good idea about LLaVA is that once the training is done, in the way that you're changing the weights of the MLP there and also the language model, you can actually pass new images through the model and get to chat with them. Because suddenly now the model understands how to align text to image. So training the AstroLLaVA, again, a work that's spearheaded by two of our brilliant peeps in UTBD, Sharaf and Mike Smith. And what they've done here, they went to the astronomy picture of the day, and they looked at APOD pictures and looked at the description of the picture, and then we created a conversation data set based on that description. And then we created this training set, and then we fine-tuned LLaVA to create AstroLLaVA. And because the AstroLLaVA is still making some mistakes that we are quite scared about, we are still evaluating the model to be released very soon. But the way the community will interact with it will be by a Hugging Face, and you can put in a very nice image of your favorite astronomical object, and then you can learn more about that particular object. So in this way, we hope to inspire the community to think about the gray beyond, as well as think about the gray research ideas that you can do with a model like this. We also have now people joining UTBD. We're going to take this to the next level with scientific applications, for example, images from JWST. Cool. So my favorite part about UTBD, apart from working with the most incredible people, is this part, the community-focused part. So how will UTBD support and inspire the community? And here we have a few projects, but I just want to mention two very briefly. The first one is called Pathfinder. This project is being spearheaded by Dr. Kartik here. He's currently a Hubble Fellow at Columbia University, and that's him right there. So Pathfinder is really looking at the archive for astronomy, and we're trying to work at the embedding space level so that we do very good question answering. And currently, I think we're running, we're trying to use AstroLLaVA as the base model behind the ROG. So what happens here, you can ask a question, and then Pathfinder brings you the most relevant papers to answer that question. It also gives you meaningful citations, and hopefully this aids our community at a very sort of absolutely necessary level, because astronomy and astronomers are still getting up to date with these advancements in machine learning. So yes, we have this already available online, and if you ever want to learn astronomy, and this is the place to go for Pathfinder. So, another project that we can do with Pathfinder is try to do this very cute visualization here where you can find islands in astronomy. So you just take the data from papers, you have the embeddings for that data set, you project them into some lower dimensional representation, and then you start for looking for patterns. So you can see here that you have the JWST value. Now we haven't done a temporal analysis, but I'm pretty sure that JWST Valley has seen emergence in the last 10 years. All right. And my favorite part about UTBD is that we can also think about, what's the space what's the space that we do not see actually. And here I'd like to talk a bit about AstroLLaVA. So AstroLLaVA is truly a variation of the AstroLLaVA that's aimed at improving accessibility for researchers everywhere. And what do I mean by that? Is that, we now live in a world where scientific output has been growing by 9% per year over the last decade. So this is, booming in scientific literature. Only science and engineering, so the field that we're in, has seen 2.9 million articles published in 2020. And this growth is increasing That's a lot. That is a lot of papers, right? And it is a struggle to keep up. Even if I just read the abstract, it is truly a struggle to keep up. So now I'll ask you to try to do this exercise. So in here, I have written an astronomy abstract, and the words have been shuffled, and the letters have been shuffled inside. The words. So the first thing that you try to do, your brain tries to do when it sees this, is try to rearrange the letters, and then try to put the words back into where they should be, and then it does the comprehension steps to actually understand what is happening. So once we do it, if we do it quite fast, we put the letters where they are. Now the words are also where we expect them to be. And finally, we are like, yes, we're starting paying attention to the comprehension step. So in this case, this abstract is talking about what happens if you have our star, the sun, being younger than the galactic bar of our galaxy. What happens if this is a scientific question for us in galactic archaeology? So if the bar is younger, the sun won't move quite as much, for example, because the bar has some dynamical effect on the sun's orbit. Okay, so why dyslexia? So I think this small exercise has already shown you why we care about dyslexia. My best friend and many of the people that I'm surrounded by in astronomy, many of them tell me that sometimes they think they might struggle with dyslexia. So it's a difficulty in decoding written language, and it's 10% in the general population, but it's believed to be much higher in the academic group. And people who have dyslexia experience things like cognitive load and slow reading speed. What is cognitive load? Means you get tired after you try to read a paper that has 50 pages in your field. So what might take me or one of my peers who doesn't have dyslexia 1 hour reading time might take a colleague of mine who does have it 2 hours reading time. So now the question emerges, what happens in that 1 extra hour? How will that 1 extra hour affect people's career long term? That is a valid question that I think we can try to solve at UniverseTBD or work in the direction of providing some solution. So why do we care? What can we do about it? We want to mitigate this problem for astronomers, and long term, we want to mitigate this problem for people everywhere. Cool. So the way we go about it, we can adapt AstroLLaVA, right? That's the beauty of these large language models. You don't have to work on the most incredible benchmark performance, but you can actually take these models and try to adapt them to something that matters for people. So we can fine-tune AstroLLaVA on some identified tasks that might help. Summarization, sentence simplification, and so on. That is, aligned with the scientific need. And then we can evaluate it and see how well it's doing by working with colleagues of ours who have dyslexia and taking their feedback and putting this back into our pipeline. And then afterward, engage a larger community so we can do this in a much more efficient and fast way. Okay, so I think that's me. I think we're done. Thank you so much. So before we finish, I would like just to say that we have our Slack channel, and that's where we sort of do the bureaucracy, very boring part of stuff. But we also have a Discord channel, which is truly community facing, and we are welcoming people everywhere to try to join us and help us in our mission. So please, if you'd like to join, please join us on our Discord. And if you want to chat with the AstroLLaVA, we have released also the AstroLLaVA chat model very recently. So it's Hugging Face, the AstroLLaVA chat. Thank you so much, and thank you for having me here.
Okay, we have time for a few questions.